If you think about a quantum computer, if you had this power, you wouldn't probably go in and tell the world that you had it.
Oh yeah, I didn't even think of that. You could just choose some public key, which holds a lot of Bitcoin, and steal it.
Who's going to notice a couple Bitcoin that everyone thought was lost a long time ago? Digital signatures are the root of ownership in all cryptocurrencies. And this is exactly what a quantum computer brings. At some point, it probably will become obvious. But at that point, it's too late to do anything.
So what does quantum now mean for Bitcoin?
Okay, great. So now we've got everyone's head spinning with the many worlds hypothesis, with superpositions, with complexity theory.
Now we get to the simple part, a blockchain.
Alex, tell me what the point is. Now this is the point. Okay, so
today's episode is sponsored by the Stellar Development Foundation and Flipside Crypto. They've partnered up to bring a series of Flipside quests to the Stellar network. Quests are a fun, gamified way to explore Stellar and to dive into its growing DeFi ecosystem. By completing quests, you can earn rewards and, of course, bragging rights with your on-chain activity score. Getting started is easy. Just grab a Stellar wallet like Freighter or Hana and click the link in the description to jump into your first quest. We kind of already started talking, but Alex, welcome to the show.
Yeah, thanks. I really appreciate you having me here. Excited for the conversation.
Yeah, same. It already started, and I think it's going to be a super interesting episode. So we're going to talk about post-quantum cryptography and kind of like adjacent topics to that. But perhaps before we get into that, two things. I think, first of all, like, what is this technology? Like, what is quantum computing? Perhaps we just give an overview first, and how did we discover it? And then I would love to hear also more about like how you got into this topic. What's your background?
Yeah. So quantum computing is a fundamentally new form of computing that leverages quantum mechanics, which is, to the extent that we are aware, the most accurate model of the physical world that humans have ever come up with, right? So quantum mechanics basically describes how things work at a very low level. And one of the things that's kind of interesting about it is it's inherently probabilistic, right? So if you think about a classical computer, a bit can take a value of either 0 or 1. Whereas quantum mechanics, because of some of its unique properties, which we're not going to get into a physics lecture here, but like what you should know about it, it's relevant to quantum computing, is that a qubit, a quantum bit, can have a value of 0 or 1, or potentially something in between, right? It's in a probabilistic way, right? So it could be 50% chance of being a 0 or a 1, right? And so because you have basically this range, qubits are kind of inherently much more powerful. Although I want to caveat that by saying, theoretically speaking, it's an amazing kind of interesting open question as to whether or not quantum computing is always better than classical computing. But for many problems, including particularly the hard problems that underlie cryptography, it's believed that quantum computers are far better than classical computers for computing those things. Like, for example, factoring, right? So factoring numbers, so, multiplication and then reversing the multiplication for the integers, that is really the underlying problem that powers the RSA crypto system, which is kind of a cousin of what we use in elliptic curves crypto. But a quantum computer, there's a known algorithm called Shor's algorithm, which can efficiently invert that multiplication and find the factors of a very large number, right? And so therefore, in the context of the RSA crypto system, you can recover a private key having only known the public key, which, if you don't know anything about cryptography, just even the words probably give you a sense here. Your private key is supposed to be secret and your public key can be known, right? But if you have a known public key from which the secret can be recovered, that's clearly bad, right? So this is exactly what quantum computers do. And in particular, cryptanalysis, or this, Shor's algorithm, is kind of a canonical example of how powerful a quantum computer could be. Another way to think about it, it's not a perfect description, but it's kind of a good layman and kind of somewhat intuitive way to think about it, is because a quantum computer exists, or consists of qubits, and qubits can kind of take many different states, or potentially can hold many different states between 0 and 1. It can kind of parallelize these operations that you have to do in sequence if it was a classical computer. That's not 100% true, but that's like a good mental model for it.
Right. But I think It's hard to talk about this without getting a bit into physics, eh? And I have prepped a bit on that, especially on the parallelization. But perhaps we park this. What's kind of like your background? Because you mentioned to me is like a wide range of things you've done.
Yeah, so I got into crypto when I was in the Army. So I started in the U.S. Army for 9 years. I was a Green Beret working in Syria and Turkey in 2015. Found out about crypto working with the folks we were training there. We were training the rebels at the time. And yeah, I was fascinated by this concept where someone who was a refugee from the conflict of Syria could potentially put their savings account in their head by memorizing a private key or a seed phrase and then go to another country and start over. That was how I got into the space. I ended up getting out of the military and attending Stanford. I was an MBA, but I was really interested in learning more about the underlying technology for blockchains. And so I was just moonlighting in the computer science school and particularly took a couple of cryptography courses from a professor there named Dan Bonet. And Dan's very, he's been into the blockchain space for quite some time. He's quite accomplished just as a cryptographer generally. And so that experience really inspired me passion for and interest in cryptography as a field. And yeah, this happened. This was kind of, so 2017 to 2019 was when I was in grad school. And this was first, there was like a big, bull market with ICOs. And then there was a big bear market, but a lot of interesting stuff was getting built during that bear market. And, it was an interesting time to be in crypto. And yeah, I was in these cryptography classes. I was running the Stanford Blockchain Club. And I ended up getting a couple jobs, first at a VC, a small VC fund. And then I worked at Coinbase briefly before ultimately getting a role at Andreessen Horowitz. So this professor of mine was an advisor, and he introduced me to the folks over at Andreessen Horowitz, and I got a job in their first crypto fund. So yeah, and like I said, it was an interesting time. This is 2019, so I remember seeing the early pitches for Solana, Avalanche, Compound, Aave, all of like the things that now these days are just like huge protocols that with wide adoption was all brand new. One thing in particular I worked on that was interesting that went nowhere, but I think will get rebooted ultimately as a concept is Libra. So the Facebook backed stablecoin. That was a fascinating experience, but yeah, one of the many things I worked on while at A16Z, but ultimately I wanted to be in the space as an entrepreneur or as an operator. And so I left A16Z end of 2020 to join a startup called Aleo. So Aleo is a decentralized, privacy-preserving, programmable blockchain, right? So basically, Ethereum and Zcash had a baby. So ZK smart contracts, and so we built at Aleo over the course of the following 4 years when I was there. So I started out as the first employee, chief strategy officer, ultimately became the CEO, and worked with Howard Wu, who's started as the CEO and then became the CTO and is now the CEO again, to launch this thing. And it went live last year. And so far, it's been really great to see it out in the wild, see how people use it, use these things for real. And I'm very passionate about, obviously, privacy, but also, again, my interest in cryptography is what led me down this rabbit hole for zero knowledge cryptography. But I left at the end of last year and was considering what to do next. And I got really interested in this problem of quantum computing. Obviously, quantum computing comes up all the time when you're studying cryptography because it's like the thing that breaks everything. But it's always very amorphous. It's not that it's usually people kind of reference it as like, oh, it's always 20 years away. Is this really a threat? If so, I don't know. So it's always amorphous, but I decided to kind of go down the rabbit hole. And what I discovered, I was like, wow, this is crazy. I guess quickly, we'll talk about it during this conversation, but I'll quickly summarize. Is first off, I think people are underestimating the timeline for when we're going to get to a cryptographically relevant quantum computer. Not as, there's obviously a whole spectrum of quantum computing that you can imagine, but cryptographically relevant is like the thing that breaks a crypto system that we care about. So I think people are underestimating that timeline. The second thing is I think blockchains in particular are going to be one of the first targets of a quantum computer. I mean, if you just look at Bitcoin, it's $2 trillion in market cap, more than the GDP of South Korea. It's like if you had one of these things, you'd be stupid not to use it for this. But I think also, and maybe the last point is that fixing these systems is going to be extremely difficult and is being heavily underestimated by everybody. And so that's why I was like, holy cow, this is crazy. So I decided to, co-found a company with some other folks in New York and London, called Project 11. And Project 11 is basically focused on applying post-quantum cryptography to secure existing digital assets, and then in the future leverage, hopefully, quantum computing and quantum mechanics to build new cryptographic primitives to make, basically new and interesting forms of encryption, new and interesting forms of, information processing or, information sharing and communication. So that's the idea for Project 11.
That is super, super exciting. I mean, I don't know where to start, but your background, I think it really shows you went after problems that you found interesting throughout your whole career there. Because like you studied the MBA, but you straight away went to go getting those cryptography classes. Joined A16Z, I suppose, right? When you said Andreessen Horowitz. And then to Aleo, and then quantum computing now seems like a meaningful mission that you're interested in. Just curious, the first pitches you heard there for these protocols that became quite big, how did you react to them? How do you view your reactions now? That sort of thing.
I mean, in venture, it's easy to look back after the fact and say, oh, of course, Solana was going to be huge. I think there were so many amazing ideas in that time that ultimately did get really big. I think I'll answer that by saying one thing that I think I maybe got a little bit wrong is I think I underestimated the degree to which a higher throughput, more scalable architecture, but less permissionless, would find a good product market fit, right? Because when I think of blockchains, their main feature vis-a-vis like AWS is permissionlessness, right? So if AWS can just turn off their servers and you can't access anymore, that was what blockchains were kind of designed to solve a little bit. And I think looking at some of the architectures of some of these more scalable networks, you can see how they're a little bit more, like there's some few more choke points. It's a little bit easier to see how that potentially problem could just crop back up, but you're still paying an order of magnitude or more than you would for just running an AWS server. So it never struck me as like, well, what's the real value proposition here? That said, I think, there are people that are very comfortable with accepting some more basically choke points or centralization vectors in exchange for more scalability. And I think, obviously Solana has defined itself by like meme coins and stuff like that. It's made it very cheap for anyone to launch a trivial token. Kind of more to the point, I think stable coins, especially stable coins that are custodial, where you already have like, you're counting on a bank to hold these assets anyway. It's like, why not just add a little bit more of an assumption around, a slightly more centralized network. So I think, that was an area that I think was hard to see at the time, but now I think it's very much been proven out. The other thing is all the founders. I mean, the best part about VC is the founders are just, it's just great to see the number of people and the diversity of people who go to start companies. It's very inspiring. My favorite company, maybe I'll just mention quickly, my favorite company that never, it did achieve pretty big success, but the one that I loved the most was Arweave. So Arweave was in the file storage space. I thought it was really cool. It was one of the investments that I backed, and still a big fan of the team.
Okay, interesting. So kind of like early on, did I understand this correctly? Early on, the concepts which went a bit more towards centralization to allow more scalability, those were not concepts that you thought would make that much sense considering the core value proposition of blockchains.
I think, maybe I'll say it this way. I think I overestimated the importance of permissionlessness for these things to have value. And I think in certain cases, it's very important. But I think in other cases, I think for other use cases, it's less important. And I think Solana is a proof of that, for example, right? I think it's architecturally slightly less. You could argue that it's less permissionless than something like Bitcoin, certainly, or Ethereum. But it's cheaper, it's faster. And so for certain use cases, it makes sense to do that.
Yeah, gotcha. So before we get into like quantum computing and the impacts or potential impacts on Bitcoin. We've seen that a bit like in a lot of news articles recently. I think it was kind of tied to some advances that Google had made on a quantum computing side. But I mentioned maybe a tiny bit into physics, so maybe it's just my own curiosity that I want to hear what you think about this. But I was listening to a podcast with the physicist David Deutsch.
Early pioneer.
Yeah, exactly. Of quantum computing. And he's also written extensively, I think, on philosophical topics like epistemology and the growth of knowledge. I'm a big fan personally. And he mentioned on the podcast how the proportion of physicists that do not support the many worlds interpretation of quantum mechanics appears to be still small. The ones that do not support the many worlds interpretation is quite big. And I think he doesn't even call it himself an interpretation anymore. He just, that's the correct explanation for him. But he mentioned how people working in the field of quantum computing, on the other hand, tend to actually be more on the side of the many worlds or Everettian interpretation. So I'm just curious, what's your view on this? Because you're working in that field. And perhaps you can give just a bit of background on this debate for the audience.
Yeah, sure. I'll do my best. It's not nearly the stature of David Deutsch, but I'll give you my take. So quantum mechanics describes a world that is very small, and that world physically has rules that are inconsistent with what we observe in the big quote unquote world, the macro world, right? So most famously, like the contradiction is between quantum physics and gravity, right? So there's no known theory that's been proven that reconciles these two things, right? And one of the reasons for that is that quantum physics has all these features which seem kind of crazy when you think about them in the macro scale, right? So I talked a little bit earlier about superpositions, right? So you can have particles which are effectively in superposition. This is like the layman's way to describe this was posed by Schrodinger. So Schrodinger is a famous physicist, kind of in Einstein's era, and he had this thought experiment, which was like you have a cat in a box. Before you open the box, like the cat could be dead or alive. It's in superposition, right? Like it's both dead and in some ways it's like both dead and alive at the same time. And so the debate that you're referencing is kind of like how to view this fact, which is like again, quantum mechanics is the most rigorously tested, most accurate physical theory of our world. We know superposition at the level of tiny particles exists, like in a very real way. Superposition is real. The cat at the micro scale is both alive and dead. And people have always struggled with what to make of that. Physicists argue about this. And this is like one interpretation is called the many worlds hypothesis, which is that basically reality is this constantly branching multiverse where everything that possibly could happen does happen in some reality somewhere in this multiverse. That's the many worlds hypothesis. Many physicists don't like it because it doesn't there's not really a testable prediction, right? We obviously inhabit one reality. It's impossible to say whether or not there are more. And so I think my understanding of the debate is that like it's a bit more of a philosophical one than a physics one, right? Because you're not, by virtue of the way this is, these quantum mechanics work, unless there's some incredible breakthrough with somehow being able to observe these multiple universes if they exist, it's hard to ever prove whether or not this is true. Obviously, there are probably physicists out there, and I know Max Tegmark is another physicist who wrote a book about this. I highly recommend his work to folks. But yeah, my view on it is, I think it's interesting philosophical debate. It seems to me that I think it's interesting to consider. I guess I'm more neutral. I think it could be true. It might not be true. I think its relevance to the day-to-day world, though, it very much is the case that quantum computing specifically relies upon this concept of superposition. And so whether or not that superposition implies multiverses is less important than that it's just a feature of our microscopic world.
Okay, interesting. Because I guess that's the tie to the quantum computing part, right? Did you say you mentioned parallelization and stuff, like there's so many calculations happening. I think that could not be done in one universe even. So like each of these are happening in parallel universes, which is a bit weird to think about, I guess. But
I mean, that's a way to look at it. Maybe I think there's also a simpler way to look at it, which is that in a quantum system, you can know more about the entire state of the system than you can about any of the constituent parts. Like that's weird, right? If you think about it, like if you think about it from the macro scale, it's like I can look at a planet and I can break down the planet into like rocks, and I can break down the rocks into like atoms. And if you understand all the little bits and you put them back together, you'll understand the planet in perfection. Quantum mechanics is not like that. Once you get below a certain threshold, there's this inherent uncertainty. Like the other example is like this, you can never, it's the uncertainty principle. So this is also Schrodinger's thing. It's right. So it's like, you can neither know the exact position, or you can either know the exact position or the exact momentum, velocity of a particle at any given point in time. You cannot know both, right? So that's sort of like, it gets to the sense where like, it's possible to know about a system to a higher degree of detail than any of these individual parts. And you can use that fact to basically build algorithms that kind of leverage this hidden information that you cannot access to then do these computations, which are impossible in the classical sets.
Yeah. And I think it depends a lot around error correction as well, or to get the right results at the end. And to do that scalably, I think is the challenge here. So we have like a cryptographically relevant quantum computer in the end that scalably
Correct.
fixes these errors. And
yeah. So we're transitioning the conversation here just for the audience to follow along. So there's like the theoretical existence of a quantum computer and theoretically how it kind of works to the practical challenge. So quantum computing, so David Deutsch was an early pioneer, Richard Feynman, and really these observations came from the fact that understanding, like computing the state of a quantum system, and say for like in a context that's physics based, was difficult inherently. And so a quantum computer was kind of first theorized as like the device in which you would need to understand the physical world, because like its architecture was effectively the same as the physical world we observe at that micro scale, right? So it kind of like it came up as like this experimental physics thing, right? Without people thinking about use cases. In fact, it didn't really it was just an experimental curiosity.
Yeah. It wasn't even called that when David Deutsch wrote that paper. I think he didn't think of it being a quantum computer. I think he was trying to achieve something else, prove something else.
Exactly. And it was only in the 90s. So people were kind of like, hey, honestly, it was kind of at the brink of being written off, or like, okay, sure, maybe there's like a way to make this, but like, does it really have any utility whatsoever? Is it better than a quantum computer? And Peter Shor at MIT famously wrote this algorithm, which now has his name, Shor's algorithm, which showed that for a problem that we believe is very hard for a classical computer, factoring numbers, then there is a much more efficient algorithmic way to do it on a quantum computer. And that was really the moment when people were like, wow, okay, there is maybe a difference between what a quantum computer can do and a classical computer do. Maybe a quantum computer is no longer an intellectual curiosity. Maybe it can do things that are inherently more powerful. And people over time have come up with a bunch of other possible use cases, like another algorithm called Grover's algorithm, deals with unsorted search. So if you have like a giant pile of things, a classical computer has to just brute force, whereas a quantum computer can kind of more efficiently navigate that search. It's not to the same degree as like Shor's algorithm, but somewhat more efficient than a classical computer. So anyway, you mentioned a second ago, going back, so theoretically these things can exist. Theoretically, there are applications for them for which there's no equivalent on a classical computer. Okay. Now there's practically, how do you bring one of these things into existence? And there are all kinds of practical challenges. And this is why I think oftentimes many people tend to view this as like nuclear fusion, where it's like, oh, okay, it's an engineering problem, but it's a monumental engineering problem. I don't necessarily agree with that framing. I think doing like nuclear fusion is literally, you have to put something that's 100 times as hot as the sun inside of a ball this size. That's extremely challenging from an engineering perspective. Whereas this is, I think, less so. I mean, there are quantum computers that exist today that scale up to 1,000 qubits, or even more probably. The question is just how to use them effectively. So error correction is one of the fundamental challenges. There are really three things that go into like building a useful quantum computer, right? Cryptographically relevant quantum computer. First off, you just need enough qubits, right? And this sort of follows if you think about computing, right? When I was a kid, we had an Atari, or I had my first computer was a 286, what we called it. It was an early Intel machine. I mean, I think it had like 64 kilobytes of RAM or something like that, right? So you just have like, you obviously are limited by what you can do based on just the number of physical bits inside of your machine, right? The more bits you have, the better, like the just more powerful, operations you can run. So the number of qubits is important, and being able to fabricate qubits. We don't have to get into the details, but you can just imagine of like a classical bit, which is only expected to take a 0 or 1, is kind of like, okay, well, I can implement that as like a light switch, which you can basically. It's kind of is a light switch. It's 0 is off, 1 is on. A quantum computer is kind of like, to fabricate this, you need something to be very, very microscopic. So like, and there's a bunch of inherent uncertainty based on quantum mechanics. So fabricating them is highly non-trivial, right? So this is, I think, one of the first 10 years of building a quantum computer is focused on this problem of basically being able to fabricate these things reliably. Which, by the way, classical computing went through this too. We all kind of take it for granted, but this is ultimately like Moore's law. The story behind Moore's law is people spending a lot of money to do this, like bring classical circuits to a smaller and smaller scale. Anyway, so there's a number of qubits. Then there is error correction, right? So in both classical and quantum computing, there's potential noise, or there are potential interference from other sources that could mess up your computation, right? Now, quantum computing is kind of, I guess the way I would frame it is like, it's much more sensitive than classical computing, because you have, like I said, you have 0 or 1. It's like pretty easy to distinguish 0 or 1. Whereas in quantum computing, you're like this very, very delicate superposition, potentially, like we used the example earlier of a single particle being a 0 or 1. But in practice, you're going to need an entire system that be in superposition with itself across maybe many, many, many qubits. And any slight perturbation of that basically causes the whole thing to collapse, and it's no longer useful, right? And so what people have tried to do is figure out how to have small groups of physical qubits, and you can tolerate some number of faults to then get to what's called a logical qubit, right? So basically, it's like you got 50 physical qubits, let's say, and I think the real number is closer to in the hundreds, but you say you have a couple hundred physical qubits. Even if a large portion of them fail, you're still going to get the right answer, right? So this is really the whole focus of quantum error correction, right? Is designing algorithms and implementing these quantum error correcting codes to be able to recover in the case of these errors that crop up in the normal course of computation. That's kind of the second challenge. And the third and final challenge is you need to basically maintain the coherence of this entire system during the runtime of your algorithm, right? So Shor's algorithm depends on how you kind of choose your constants and allocate your resources, but it can, you can potentially do it quickly. You can do it over a longer amount of time, but use less resources. And your quantum computer has to basically be coherent. All of these qubits have to be in, your superpositions have to stay together. Everything has to stay together for long enough for that computation to give you a useful answer, right? So this coherence piece, and this coherence is also related somewhat to like the control, right? This is one of these interesting things about the system is controlling it or measuring it has an impact, right? Whereas, and this is another weird thing about the quantum world versus the classical world, right?
Because when you measure it, it's either 1 or 0.
Exactly. You're never gonna get an answer like, well, it's 50% 1 or 0. If you measure it, this is intuitive, right? Like the classical world, there isn't this weird thing. But this is called collapse, right? This is like collapsing the state of the system into one or the other. Now, experimentally, if you run this many times, you'll find that like you get those probabilities, which are predicted in quantum mechanics. The bottom line is for the system to produce a useful computation, it can't collapse too early, right? And so this coherence piece is really the third thing.
Yeah. It's a fascinating area, and it's confusing all the same. So you mentioned like factoring is sort of like at the core of cryptography, right? Like, and correct me if I'm wrong, I'm not an expert there, but it's the way I understood it was to find like the smallest prime factors that you can multiply to get that result. And to find these factors is not a trivial computation. It takes a lot of resources. And quantum computers are now more efficient at finding these. Is that another way to put it as well?
Yeah, the way I would, so there's two related algorithms that are based on slightly different assumptions, but I'll try and provide an explanation that covers both. Generally speaking, in mathematics, there is this interesting, there's a whole category or there are whole classes of problems that are kind of efficient to compute one way, but less efficient to go backwards, right? So there's no known algorithm. Like algorithms to go one way are known to be efficient, and algorithms to go the other way are known to be not efficient. So, for example, factoring, which is fundamentally what the RSA crypto system is based on. So RSA, which is kind of the first public key cryptography crypto system, is based on this. You basically take two numbers, one of which is prime, you multiply them together, and you get a really huge number, right? And that's like pretty fast. Like, I mean, obviously, if we're talking really big numbers, you're not going to do it on paper. But for a computer, it's relatively fast. Whereas, like, breaking down the constituent parts of that huge number is very difficult, right? And without getting into too many of the details, the ability to kind of break down or understand what the constituent parts are is kind of really what's related to your private key, right? Now, the reason it's hard is you can kind of think about it intuitively. Like, there's an algorithm to do multiplication, but how do you find factors? Well, you kind of just got to try them all. You're like, okay, well, is this divisible by 2? No. Okay, is 3? You know, if you have like a 50-bit number, or in the case of RSA, these are 4,000-bit numbers, it's going to take you longer than the age of the universe to ever factor it, right? And this is that inherent hardness of that problem is exactly what crypto systems are based on. It's easy to multiply and get this huge 4,096-bit number, but it's really, really hard to go backwards. Similarly, in elliptic curve cryptography, which is more relevant to most blockchains, I'm not going to get into like the mathematics behind elliptic curves, but just understand that it's effectively the same idea of inverting multiplication is hard. Multiplying one way is easy. Inverting it is hard, right? Now, Shor's algorithm gives you a way to efficiently invert multiplication in this context. And that is why it can break these crypto systems potentially. And this is like, to be clear, this is an algorithm. It's not like, you can instantiate it many different ways, but algorithmically, there is no known classical equivalent that can do it as efficiently. By the way, maybe it's just a quick aside, just to speak on like the kind of quote unquote philosophy or, a quick detour to complexity theory, right? So computational complexity, like this whole concept of whether or not hard problems exist is based on this notion of P versus NP. So P in computational complexity theory, the P is the class of all problems that you can like easily verify in polynomial time, say, and then NP is the ones that are compute in polynomial time. And NP is the ones you can verify in polynomial time. Basically, it's like things like factoring numbers. We think there is no algorithm for, but we can't prove classical algorithm for it. We can't prove. So these like this equivalence, and this is like the point of this is that like if it is true that P equals NP, that everything that can be efficiently computed can also be efficiently verified, then that means there really is no basis for any cryptography, right? Because like you need these one-way functions effectively. So Shor's algorithm is basically an example of a quantum algorithm that is unique in that it has no classical equivalent.
Right. So what does quantum now mean for Bitcoin? Everyone hears quantum is like 10 years away. What's your take on this and when it might really become problematic?
Okay, great. So now we've got everyone's head spinning with the many worlds hypothesis, with superpositions, with complexity theory.
Now we get to the simple part, a blockchain.
If you fast forward, now you can start me. Okay, just Alex, tell me what the point is. Now this is the point. Okay, so I mentioned these 3 challenges: number of qubits, error correction, coherence. Right? There are a number of different approaches, a number of different teams building different types of quantum computers. It's unimportant how they're building them. The point being is there are many different ways people are trying. In general, qubit count has become, I consider it to be more or less a solved problem. Like it's no longer the bottleneck. Error correction was a major issue, but at the end of last year, Google announced this result called Willow. They demonstrated with a quantum computer they call Willow that you can use error correction to suppress errors, and that error suppression gets better the more qubits you have. That was a real breakthrough because because of that, now you can actually see a world where it's like now you can build more qubits and actually get more interesting potentially results. Exactly. And so now there's still this kind of whole problem of coherence. But the thing I want to highlight in the relevance to your readers around like, okay, timeline, this is not like, there's a world in which a breakthrough happens here in the same way that it did error correction, and quantum computers could just be around the corner. There's another world where this becomes a harder problem than people expect, and it takes a little bit longer. This is why if you like Google or you ask ChatGPT right now, when is a quantum computer coming? You're going to get answers that range from like 5 years, probably on the most, optimistic, to like 50 years or never. So I think there's a huge range if you survey the experts. Roughly speaking, I think a good way to consider it is like NIST, the National Institute of Standards Technology, that's in charge of developing post-quantum cryptography that should be used by industry and governments, at least in the US, has said, hey, 5 years from now, all crypto, any critical system that's relying on classical cryptography needs to transition to post-quantum cryptography. And 10 years from now, classical cryptography is entirely deprecated. So now that's their timeline. So, and I think that's like a good enough one to plan on. And obviously NIST, there's been a relationship between NIST and the NSA before. Does the NSA know something that we don't about quantum computing? Who knows? Point being is like, that's probably, I would consider like 10 years is the middle of the range. But I think again, the important thing is that it could happen much sooner. I think the other important thing that's very relevant to Bitcoin, now we're going to get kind of into the game theory around this. I just published a blog post about this, we can link to here if people are interested. But if you think about a quantum computer, it's likely going to be pretty slow at first. It's likely going to be pretty expensive at first. And you're going to want to get your investment back from that very long, hard effort. Now, if this is a government that's using it, they're probably going to be focused on intelligence gathering at first, potentially. But in either case, but they're not going to want to reveal that they have it, right? Because if you reveal that you have it, then people are all going to switch over to cryptography that day. That is, that's not vulnerable. If it's not a government, if it's a private entity, kind of the same deal. Like, I think in particular, if once you get into a company, you maybe end up in a world where now you have an economically motivated actor. It's like, hey, I've got this quantum computer. How do we make money for it? There's a lot of speculative use cases for quantum, like optimization and stuff, but it's not clear how much that's worth. Whereas I can just go to the Bitcoin blockchain and I can tell you exactly how much one of Satoshi's keys is worth right now, right? And by the way, Satoshi is dead, not, gone. Maybe they lost their key. Like, is it even stealing? I don't know, right? And so, but here's one thing I do know: if you had this power, like, how would you use it? You wouldn't probably go in and tell the world that you had it. You would maybe just look for something that you think no one would notice, and then you would recover it.
Oh yeah, I didn't even think of that. So you could. I was going to ask you something like that. If that level was reached, would there be a sudden public awareness of it? But no, you could just choose some public key which holds a lot of Bitcoin and steal it.
You're not going to know. Honestly, the most naive thing to do would be to try and move Satoshi's, because he's widely believed to be dead or gone. But if you were slightly less naive, you would just pick any one of the other 6 million Bitcoin that sits under an exposed public key, and you would just move that. And it's not going to look. The thing is, it's the term that's used is forgery. A quantum computer can forge a signature. It's not even really right, though. A quantum computer can just recover the private key. And because you can recover a private key, you can produce the real signature, and a signature is ownership, right? So if I gave you my private key to my Bitcoin wallet, or you had a quantum computer that was able to get my private key from the public key, those two worlds are indistinguishable, which means that like, you're not going to be able to see this. You're not going to be able to tell at all. It would just look like every other digital signature that hit the blockchain. The only way you would know is if someone basically announced it, either by going after something obvious like Satoshi's coins, or they just told you. But there's no reason to do that, right? And again, maybe someone will, because it's like the first person to come up with is like a researcher or something. But like, in a world where it's a company, I think, who's going to notice a couple Bitcoin? that everyone thought was lost a long time ago. Could be worth a lot of money, right? Now, the key implication here that I want people to take away from this, because this is very important, this is what ultimately got me down this rabbit hole. Digital signatures are the root of ownership in crypto. And by the way, this goes far beyond Bitcoin. Every single cryptocurrency is based on this idea that the ability to produce a digital signature means that whoever did produce that signature is the owner of the asset. This is universal across all cryptocurrencies. Like we were talking earlier about permissionlessness. I think everyone's got their own definitions of permissionlessness and centralization, but all cryptocurrencies share this feature. And this is exactly what a quantum computer brings. In a world where a quantum computer exists, you cannot trust a digital signature to mean ownership. And what does that mean? That means, and to put these two together now, I have a quantum computer. I'm not incentivized to tell anybody. At some point, it probably will become obvious. But at that point, it's too late to do anything. Why is it too late to do anything? Well, let's just imagine a scenario with Bitcoin. Bitcoin's like people are, quantum adversaries moving Bitcoin around. 5 years later, we all find out. Well, now what do we do? Well, we've got to migrate to some secure version of this protocol. What does migrate mean? Migrate means, well, I have to show you that I have some Bitcoin in this world and we need to go to this world. But if I have a quantum computer, I can just pretend to be you and migrate your Bitcoin to the post-quantum world, right? So at that point, the concept of ownership is entirely arbitrary.
So migration has to happen beforehand, or as soon as possible, because you showed me the tool that you guys have.
Yeah, exactly. So this is the tool that we built at Project 11, which is basically just describing in simple terms. This is a way to bind a post-quantum signature. So you generate a new post-quantum key. It's worth maybe as a quick aside, there's a whole bunch of post-quantum cryptography that's been standardized that is based on different assumptions, which are believed to be hard for a quantum computer. Okay, so NIST has worked on that for the last 10 years. Every single blockchain of the future is going to have to be based on one of these. And that's going to involve a bunch of deep protocol changes, which is going to take a long time, which is another reason why the communities need to all start now. But as an individual, to solve this migration piece specifically, what we build is basically an ability to bind an existing UTXOR address to a post-quantum key pair. This post-quantum key pair doesn't have to correspond to any asset on a future blockchain yet. Its main importance is to recover this property that we lost, which is that signature does not equal ownership. Now you have two signatures, and you can say, in a world of what will likely be chaotic, you can say, hey, the owner of this digital asset is the one that can produce both the classical signature and this post-quantum signature based on this claim that I made back when we thought there was no quantum computer, right? Now, obviously, this is fuzzy, and the further in the future you get, it gets even fuzzier, going back to the point that I made earlier that you may not know when a quantum computer is there. So that's why it's critically important to start this migration process now, and that's exactly what we're starting with Project 11. This is our product, the Yellow Pages. So yellowpages.xyz. So for anyone who's interested, specifically for Bitcoin.
Yeah. And like you mentioned, we don't know when that time will come because inherently it's dependent on the growth of knowledge, right? And the growth of knowledge is unpredictable. We don't know when there'll be some breakthrough, when we'll reach the number of qubits. Will it be an incremental step? Will it be a qualitative step in knowing something new where you can suddenly have a lot more qubits? So yeah, that's really, really interesting. So speaking of that, what's Project 11's Q-Day prize?
Yeah, so we talked about Yellow Pages. So Yellow Pages is a product to enable individuals to basically bind keys to post-quantum equivalents and then effectively have a claim over digital assets today. Q-Day prize is another initiative that we have, which is all about basically creating a canary for how close we are, right? So, like I said a second ago, a true quantum adversary is not going to be interested in revealing that they have a quantum computer that can break Bitcoin. But we don't think we're there yet. But what we would like is to kind of have an understanding of how close we are. Kind of see if we can get some real-time feedback, right? So the idea of Q-Day prize was basically to create this canary, which is the statement is as follows, is break the largest possible public key with a quantum computer today for 1 Bitcoin, right? And so, I think state of the art, roughly speaking, that people expect is around, I don't know, in the tens of qubits or in the tens of bits of public key, right? So Bitcoin public keys are 256 bits. the state of the art for breaking a public key with a quantum computer today is probably around 25-ish bits, we expect. So that's good. And then, so someone who can do it for 25 bits can now earn a Bitcoin. So there's no way they'd make any money off of quantum computer that can factor a 25-bit number today. But now the community and the world has a benchmark potentially for the lower bound of where things sit. I mean, we assume there's someone who's doing secret stuff who's up higher, right? But now at least you have a bit of a lower bound on how things are advancing. And the plan is to have this to be a recurring effort that we do in collaboration with folks across the quantum computing community, as well as the crypto community. And really, this is just, the point is to be able to, as a tool, it's to give us this canary as a tool to help us all plan for the transition, since it will definitely be disruptive and go to the root of every single protocol and likely take years. Just as a quick plug on the info, if you want to learn about that specifically, Q-Day Prize is not, I think it's linked on the Project 11 website, but qdayprize.org is the link for that for folks who are interested, who want to actually try running Shor's algorithm on real quantum hardware and seeing how big of a key they can factor. qdayprize.org is where you can learn more about that.
That would be cool. And it hasn't been cracked yet.
So we're taking submissions. We're basically, over the course of the next 9 months, we're going to take submissions and we'll have judging at the end of the 9-month period, and then we'll inform the winners of who won.
Gotcha. And just to go back to the binding, so you bind with your solution there, you bind the Bitcoin key to a post-quantum key. And then the idea behind it is that in the future, when there'll be like social consensus formed around to what fork to move, which mapping between new key will map to the old key, that they then say, okay, for example, people who did use your tool a few years ago should be able to have that mapping, that access on this new Bitcoin chain, or?
Yeah, it's the basis of social consensus, right? I can make a Bitcoin fork right now and use zero knowledge proofs, but there's no one on it, right? So the Bitcoin of the future is going to be determined by the holders today. And by empowering those holders, both individuals and institutions, with a way to basically make this post-quantum cryptographic claim, you're starting to lay the tracks to that future protocol that you have to go to. And by the way, it's important to note, there's a couple different versions of that world. Yellow Pages, actually under the hood, you generate 2 signatures for 2 candidate algorithms that have been standardized by NIST, because it's not quite clear yet which of these 2 will be better or will be ultimately implemented in the Bitcoin protocol, right? But I think the important thing to note is that going the inverse direction, I think is there's no point, right? Because I can describe a future post-quantum Bitcoin, but unless there are people on it, it's not Bitcoin, right? And I think this is maybe the last interesting implication that I would leave your listeners with is crypto has come very far from when I started in the space. I mean, I remember when I started, 2015 was when I first learned about it. I remember when I started at A16Z, there was legitimate talk about whether it would be banned. Now you have big banks that hold this, made, huge amounts of institutional money that's come into the space. BlackRock issues ETFs on the basis of not only Bitcoin, but Ethereum and other chains probably, many more soon. This has become heavily institutionalized. The players around the table, backing up. The change that we're talking about here is incredibly fundamental. There has not been a blockchain. There's not been a fork in the history of crypto that is anything like this. It is so fundamental to everything. We've been spending most of this time talking about Bitcoin. Let's talk about ETH for a brief second, or any smart contract blockchain. Those have it even worse because we're talking about individual keys. How do you secure a smart contract that was deployed 5 years ago by someone who left, but still has millions of dollars of liquidity in it? How do you migrate that? It's who the hell knows, right? The point being is this is going to be extremely disruptive, and the owners of these assets, which today more than ever include big institutions, they have the most to lose and are going to have a very big say in what happens, which is why, again, I think the right way to start addressing this problem is to go to the end owner, the end asset owners, be the individuals or be the large institutions, and say, this will happen. And if that happens, the value that you hold could be worth 0. And let's start by solving that problem and then work backwards into what we think the future needs to look like. And that's our whole philosophy of Project 11.
So what if we would not wait around and migrate some of these protocols to post-quantum cryptography now? I'm just thinking, for example, I believe Bitcoin has a unique problem there around, because Bitcoin's strength is a bit like not upgrading much and keeping things the same, and that might make it also slow to make an adjustment here. For example, Polkadot, I believe, has forkless upgradability, so they're doing like dozens of upgrades per year, I think, without forking the chain. And I had heard that it would be relatively straightforward to bring quantum resistant cryptography then to the chain. So just wondering, what's your take on this?
Yeah. Look, first off, my take on the last thing you said, whenever I hear a crypto network say that some major cryptographic upgrade is going to be relatively straightforward, I take it with a big grain of salt.
Yeah.
I think, like I said, this goes to the root of public key cryptography. So, I mean, there is not a more central thing for any blockchain. Different blockchain communities have different cultures that are more or less open to changes and are more or less centralized in terms of their governance. As you pointed out with Bitcoin, it's kind of like some people view it as a feature. They're like, hey, this is never going to change. And there's like no organized governance. Like if anything ever happens, it's like some kind of theoretical bottoms up thing, right? On the flip side, you imagine like on the other end of the spectrum is like a bank, not centralized at all. They want their cryptography is vulnerable too, but theoretically they just need to flip a switch and implement the new stuff. And then everybody's using the new stuff, right? I think the key thing here that I would say for every blockchain network is that sure, Polkadot, let's say, might be able to upgrade its protocol. But every single individual dot owner, unless they migrate their address, they're still vulnerable, right? Because your address is derived from your public key, which is public on the blockchain, right? That's like, unless there's some way of like having, and some privacy preserving blockchains have this, like, where this is like basically a mask over your public key. By the way, Bitcoin has this to an extent. A lot of the addresses are this pay to public key hash, which is basically, it's not the public key itself, it's the hash of the public key. So those, in many ways, Bitcoin is already more quantum resistant than many chains. A lot of them, like, I'm not actually familiar with DOT, but Solana, for example, like the address is just your public key, right? So for Solana, for you to be secure, it's like, even if Anatoly says, hey, we have a new protocol, unless every Solana holder migrates, then there's still vulnerability, right? So that's why I don't think it's going to be straightforward. The other reason I don't think it's going to be straightforward is like to migrate over to this stuff comes with real issues. And Bitcoin and the smart contract chains kind of had two distinct considerations. Bitcoin has to contend with the fact that these signatures for post-quantum algorithms are very large generally, right? So the two NIST standardized candidates have signatures anywhere between 20 to 100 times the size of existing ECSA signatures. What does that mean? That means like for you to keep everything the same in Bitcoin, blocks would need to go up to 20 megabytes per block. Last time Bitcoin contemplated a 2 megabyte block size, there was a hard fork. So, your listeners can form their own opinions about what will happen when a 20 megabyte block size is proposed. Then there's the hard question of what do you do with this? What do you do with the unmigrated Bitcoin? What do you do with Satoshi's coins? Do you burn it? I mean, you can't move it, right? Like, I don't know his private key. I can't move his crypto. So do you burn it? Do you reallocate it? Do you let the quantum computer get it? Those are the only three options for any crypto network. There is no fourth option of like somehow migrate it for it. Like, if your listeners take one thing away from this podcast, it is no one can migrate your crypto for you. You must migrate your own crypto, period. Not Satoshi, not Anatoly, not A16Z, no one. It has to be, if you own it, your self-sovereignty implies that you must do it. And there's, of course, people that aren't going to. And that means real money is going to have to be destroyed or reallocated or confiscated, right? And that has, just that alone has enormous legal considerations, right? That's why I think this hand wave that some people make, when like, it's going to be simple, is crazy. On the smart contract side, I think the one other note I would make is that in addition to being large, some of these signature algorithms are slow. Well, Solana, for example, we talked about earlier, is really predicated on this idea of fast block times and rely upon a bunch of nodes to quickly produce and verify signatures. When you're considering signatures that take potentially seconds instead of microseconds to verify now, you're going to have a massive impact on the throughput of these blockchains. This is why it's not going to be simple. It's going to be simple, maybe in theory, to imagine a post-quantum blockchain, but turning an ecosystem and a network with billions of dollars of value already on it into something that's post-quantum, I would push anyone against saying that's simple. And I think this is exactly why, if you think about NIST's timeline, which says, NIST says, hey, all banks 5 years from now have to migrate off classical crypto. That's banks. Arguably, blockchains are more vulnerable than banks. And so if we're going to even have a hope of doing this partially in 5 years, we need to start right now. And realistically, it will probably take even longer.
Yeah, straightforward was the wrong word. I think that there was a path towards it, or that there's been being worked on it.
No, and I know this wasn't your words. I mean, people, I hear this sentiment all the time. People are like, it's not going to be that hard. I think if you think about what this takes, I think it's going to be very controversial, and controversy means no consensus, and blockchains entirely are built on consensus.
Oh, that's a great point. Yeah, the consensus around this issue will be a problem. So maybe to wrap this up, I'd be interested to ask again, like, what are you then concretely working on at the moment that you're excited about to kind of make blockchains safe for this post-quantum world in a way? That's basically it. And are you optimistic?
Look, I mean, something is going to survive, right? I don't think it's going to look anything like what people see today. And I think how much value goes from the present into the future is entirely dependent on how much people prepare. And I started my career, I learned about blockchains for like refugee use cases. And it's incredibly important to me. This technology, I think, represents a true breakthrough in the sense that the human impact has largely been positive. And I think these technologies should continue to exist. That's why I'm working on this, because I think this is an existential threat to every blockchain. But I think ultimately blockchains will survive this moment. I mean, there are some blockchains that are quantum resistant already that no one uses, but I don't know, maybe those will be the Bitcoins of the future. I would prefer though to avoid the chaos that I think would ensue if we didn't prepare at all. And so that's exactly what we're doing in Project 11. We're helping people, protocols, and institutions prepare for this moment. Like I said, starting with the most basic thing. Reclaim your self-sovereignty. That's what the Yellow Pages is. You now have a signature and a claim over assets today that is the best guarantee you're ever going to get. That you can do that before a quantum computer exists. The next step is to make that slightly more robust and build effectively tools that start to provide real insurance against a potential quantum computer coming after you, your assets specifically. This is more relevant for institutions. And then we want to contribute to primarily Bitcoin, but we're open to contributing to other ecosystems too for testing these new protocols and the assumptions that underlie them. So having launched a blockchain, I know everything is simple until you try and do it. And that's why I think it's going to be really important that you have a focal point, an organization that is contributing, like a testnet, for example, for post-quantum Bitcoin. And I think that will be incredibly important for the community to observe and learn from as we consider collectively, because this is Project 11 is not Bitcoin, right? Project 11 is not, it's a community member. But collectively, we need to make decisions based on the best information we have available. And I think once we get to that point, then I think that's when the hard work and consensus building can really start. But to end on what I'm really excited about and other stuff that we're working on in parallel, we've spent this whole conversation talking about quantum computing being like the end of the universe for blockchains. I want to point out that
all of the universes.
Yeah. I want to point out that quantum computing is incredibly exciting. This is a powerful new paradigm. And we talked about Shor's algorithm. And I mean, there are other interesting algorithms that actually are better cryptographic, that enable better cryptographic primitives. Let me just give one example. if I want to share a key with you, like let's say a private key for encrypted messaging chat, the only way to do that today is over a classical channel, and there has to be like a lot of public key cryptography is used to ensure that key is shared securely. You can actually use quantum mechanics and this entanglement property to enable you and I to share a key without ever having to go through a classical channel. In fact, this is actually what China, they just announced that they're like building their future communications network around this exact principle. So this is basically called quantum networking. So quantum networking leverages some of this inherent properties of quantum mechanics to enable something that's more secure. It's more secure because if this information is never sent over a classical channel, it cannot possibly be intercepted, right? And it's leveraging this weird nature of entanglement in quantum mechanics to kind of do the communication in a totally, robust way. That's just one example. By the way, that's been known for many years, right? There are other examples of quantum mechanics that you could imagine turning into new cryptographic primitives. And this is fundamentally what cryptography will turn into, is it will be the basis of it, I think, will ultimately largely be on this foundation of quantum mechanics. Because again, these are the problems that are associated with quantum mechanics, and the properties of quantum mechanics reflect the world in which we exist, right? So in some ways, it's sort of that's why a quantum computer in some ways is sort of the perfect theoretical computer, right? It really is down to the lowest possible level, a representative of the physical world. And so that is really the long-term vision for Project 11, is we want to be the Netscape of the quantum era, right? And this yellow page is just the first step. This is like the first baby step in that direction. But ultimately, I hope we have products that are basically the interface for individuals to share keys, to, have like quantum money schemes, all this new stuff. We really want it to be at the epicenter of as Project 11.
Once the cat is out the bag, or out of Schrodinger's box.
Yeah, exactly.
There you go. You guys want to be the leaders in this. Yeah, I think that's amazing. Alex, thank you so much. This was super illuminating. One of my favorite shows for sure. You're welcome anytime.
Cool. Yeah, this is a lot of fun. Thank you so much for indulging me and let me expound on all these interesting issues.